Okay, for lesson number 16 here, we're going to do project number 4, and that's to build a simple direct conversion receiver. And I'm going to give you 3 options, and you can even add some more yourself. Option number 1, go to Experimental Methods in RF Design, Chapter 1, Figure 1.9, and this is a direct conversion receiver for 7 megahertz. And it only requires 2 integrated circuits, 1 mixer, AA7FO, and you can get these pretty cheap, and the LM386, which is also a cheap IC. AA7FO is obsolete, but you can find them some places. You may have to get it in a SMD part and use a breakout board or whatever to, make it an 8-pin dip. But anyway, one of the things about this circuit is that it uses a 5 to 6 volt source. 5 volts you can get with a 5 volt regulator. 6 volts you can get with a Zener diode. But it's just an odd voltage. I'm going to give you a second option here in a minute. But this thing is set up for receiving pretty wide spectrum on the 40 meter band. Thing is, it's not going to be a very sensitive receiver. One of the questions I have is if you could build this receiver, and I built one Manhattan style. I have to dig it out of the drawer, see if I can hear W1AW at night. But anyway, this is a simple one. That's option number 1. Make a little board or do it ugly style, use a non-solder prototyping board, any of the options that you prefer. That's option number 1. Option number 2, go to your favorite browser and do a search for DC for direct conversion receiver PDF. And one of the options that's going to come up here is wherever HF5 is. I'm not a DXer. I got my first license in 1957, and I don't think I have DXCC yet. But this has a part of Doug DeMau's book, and this is DC Receiver Design Notes, and it's available several places on the internet. But in here, there is a direct conversion receiver schematic. There it is right there. And it's similar to the one that Wes Hayward et al. Did. It's got an AA602, got the LM386, but you add another amplifier stage here for the audio frequency. Now, the DC receiver is pretty easy to understand. Here you've got a bandpass filter, which restricts reception on 40 meters. You don't want all the other stuff coming in and causing interference. You still may get some interference if you've got a local strong AM station, broadcast station. Anyway, bandpass goes in here. Here's your local oscillator, and this is going to oscillate on the frequency that you want to listen to or near to. And what happens, let's say this is a CW receiver, or you can do it for sideband, but say someone's transmitting on 7.023 megahertz. That happens to be the QRP frequency in China. And I bought a Frog, a little transceiver, simple one. It's crystal controlled, and it's at 7.023. Anyway, say somebody's transmitting a 7.023. If you have this oscillator oscillating at 7.02 to 4, then the difference between that frequency and the local oscillator is 1 kilohertz, and that is the tone that comes out of the output here, pin number 5. Now, the 7.023 and the 7.024 or 27, whatever it was, what did I say? If we have 7023 and 7024, both of those are also coming out here, but you can't hear them. The only thing that you're going to hear for the rest of this circuit is audio. So you're going to get a 700 or 1 kilohertz tone come through here. This 10 nanofarad here, 0.01 microfarad, is a low-pass filter. I had to do the math here. It's 1 over 2 pi LC, so as the frequency goes up, this becomes a smaller resistance and it attenuates the signal. So anyway, you get 1 kilohertz in here. This is going to amplify it 3 to 6 dB, maybe more, and then you get amplification here with the LM386. The audio control is here, and you get this output to your speaker or headphones, whatever. Now, what I want you to do, everything from here out is audio, so there's nothing to change if you want to go to a different band. Now, I want you to think about 20 meters. I want you to change this bandpass filter here for 20 meters, and then get this oscillator circuit here to oscillate around 14.0475. That's the practice frequency W1AW bulletins, code proficiency test, etc. are done on there. And I've noticed on my SST and also looking on the internet that even late at night, when you can tune across the 20 meter band and not hear a single signal, W1AW will be booming in. So the band's open at night, just nobody's on. You're all asleep. Okay, that's 2 options. Oh, now I redrew this circuit here. And this is what it looks like the way I drew it. This looks more like an amplifier than it does in the original W1FB schematic. And I've put all the values in here for 40 meters. And I want you to do the calculations and check these values for 40 meters. And then what would you change here to get this to bandpass 14 megahertz? I would probably go to a T50-6, go to kitsandparts.com and look at the toroid information there. 1, that's where I buy all my toroids. Number 2, there's a calculator there that you can do the calculations to determine the impedance. Then what values do you need here to get 14 megahertz? Also, you'll notice that I upped the voltage here to 7.5. This NE602 will go up to 8, a little over 8 volts. So up in this, I think we'll get a little more gain. So that's choice number 2. Number 3 is, once again, to go to the internet, bring up your browser and go solder smoke DC receiver challenge. Let's see. I think this is it. And here, there's a YouTube channel. Look at their past episodes where they talk about the DC receiver and how many people, hundreds, have built it. This is an advanced project. Now they built it Manhattan style, and you can do that. But I think I'm going to get some time to build one with the toner transfer. So that's my ideas for project number 4. It's optional. Nobody is forcing you to do this. If you've never built a direct conversion receiver, it's just a simple exercise and pretty easy to do. So thank you for your time. I hope you will participate here, and I will see you on the other side of the logbook.